This rural structure highlights a stark physical contrast. For decades, locations like this, far removed from terrestrial fiber optic cables, were isolated from high-speed connectivity. Starlink functions as a continuously coordinated global system of spacecraft, ground stations, and lasers, rather than a collection of independent satellites. Traditional satellite internet relies on geostationary orbit, with spacecraft positioned 36,000 kilometers above the Earth. While a single satellite at this altitude covers a massive footprint, it imposes a strict speed limit. A signal takes about a quarter of a second to make the round trip, creating a noticeable delay for real-time applications like video calls. Dropping altitude to 550 kilometers shrinks signal distance. Latency drops to 20 to 40 milliseconds, rivaling fiber optics. But maintaining this orbit requires satellites to travel at tens of thousands of kilometers per hour. They speed into view and vanish in minutes. Achieving fiber-like speeds from space is a logistical challenge of tracking and predicting the paths of a constantly moving global swarm. Fielding a swarm of that scale requires a manufacturing approach tailored for mass production. Engineers utilize a compact, flat panel geometry to simplify both construction and storage. This flat design maximizes the payload volume of the Falcon 9 rocket. It allows dozens of satellites to be stacked directly on top of one another, utilizing nearly every cubic centimeter of available space inside the fairing. Once in orbit, the entire stack is released into the vacuum of space. Dozens of these flat panel satellites separate simultaneously, slowly fanning out as they drift away from the launch vehicle. They do not stay at this initial deployment altitude. Over the following weeks, onboard ion thrusters, powered by krypton or argon, actively push each satellite into its final operational position. This technical diagram illustrates how the constellation is structured into orbital shells. Satellites are distributed across specific inclined planes at a precise angle to the Earth's equator. Overlapping these planes ensures multiple satellites pass overhead simultaneously, providing continuous coverage. Measured, this carefully choreographed orbital mesh is ineffective if the ground user cannot seamlessly hand off their connection between the speeding nodes. The tracking problem is solved by the phased array user terminal. Notice the flat, stationary surface. Unlike traditional satellite dishes, there are no mechanical motors or gimbals physically turning it to follow a signal. Instead, it uses electronic beam steering. The dish digitally adjusts its internal antenna face to lock onto a satellite, then instantly hands the connection off to the next one as it enters range. In a standard data tourney, your dish sends a signal to the satellite, which then beams it back down to a nearby terrestrial gateway connected to the local internet. This path fails over the open ocean or polar regions. In these areas, there are no ground gateways within the satellite's field of view to receive the transmission. To bypass the need for local ground stations, newer satellites use optical inter-satellite links, commonly called space lasers. Infrared lasers allow data to bounce from satellite to satellite, traversing the globe until reaching a distant ground gateway. Routing through a vacuum offers a physical advantage. Light travels 50% faster in space than through a terrestrial fiber optic cable. By routing data laterally through the vacuum of space, Starlink functions as an ultra-low latency planetary backbone, sending information between continents faster than buried cables. The newest engineering frontier is direct-to-cell service, which configures the satellites to operate as orbiting cell towers for unmodified smartphones. Establishing that vital link requires overcoming severe motion distortion and processing the weak antenna power of a standard mobile phone. Sustaining this volume of traffic requires managing orbital congestion. Satellites are built with a 5-year hardware lifespan and utilize autonomous propulsion for collision avoidance. When a satellite is decommissioned, it enters the atmosphere. Aerodynamic friction causes the aluminum chassis to vaporize into plasma, leaving no debris behind. Managing this cycle relies on software-defined networking. Autonomous systems coordinate millions of active lasers, dishes, and gateways in real time. The current 800-kilogram satellites represent an intermediate limit. Future bandwidth demands will require larger, more capable spacecraft. Expanding the constellation depends heavily on the Starship launch vehicle. Lifting 10 times the payload of a Falcon 9, it is the prerequisite for scaling. Starlink demonstrates that the physical limits of low Earth orbit can be managed by a synchronized global mesh that is constantly being renewed.